everyone, my name is Shulin Zeng. I'm a postdoc at the Department of Electronic Engineering, Tsinghua University. Today I will give a talk about enabling FPGAs for efficient generative AI inference. And today I will introduce our latest work on using FPGA to accelerate large language model and video generation model inference. So today I will start with the general AI roadmap. Artificial intelligence aims at solve a specific task using algorithm models and input data. So we can express AI as a mathematical model of y equals fx. The development of AI has gone through 3 steps. The first step is the computation-based AI. At this step, we perform fx based on the human-defined rules. And in the recent 20 to 30 years, AI enters the second step, that is the perception-based AI. At this step, AI automatically learns rules based on data and fits the computation of fx, such as neural network. And finally, we believe AI will evolve to the cognition-based AI with the capability of intuitive and deductive similar to human brains. And AI will focus on discovering the relations between different things. Now, the AI 2.0 era has come. The difference between AI 2 and AI 1 is that the AI 1 uses dedicated models for discriminative tasks. For example, we can use NLP for language processing and also CNN for image classification. While the AI2 uses a general model for generative tasks with fine-tuning to adapt to different scenarios. For example, ChatGPT is using transformer-based LLMs to do different kinds of text and image generations. So, what we have done in AI1 is that we use a software and hardware co-design methodology to accelerate DNN models. The basic idea is that we co-optimize the software and hardware to gain a better peak performance, a higher utilization, and also to reduce the workload. So back in 2015 to 2020, we have done a lot of work, including neural network compression and AI compiler, and also instruction-driven based accelerator and processor, and also an end-to-end design framework to accelerate DNNs on FPGAs. So when we come to the AI2, what have we seen? So first of all, LLM in the cloud will continue to expand to a larger size to meet the needs of multimodal tasks. Secondly, with the advancement of technology, the knowledge density of models will continue to increase, and we are expected to build small devices with 4.0 or 0.1 capability through pre-trained small models. And the model size can be reduced to 3 to 13 billion models, and to adapt to the hardware resource constraint of device. And then on the right side, for LLM inference in edge application scenario, the inference capability will need to exceed 100 tokens per second in the future to meet the requirements of real-time application. For example, autonomous driving, drones, and embodied AI, that is different kinds of robotics, right? And this development trend indicates that edge devices will no longer rely solely on the cloud for inference and can independently complete more complex tasks. thus providing more efficient and greener solutions for scenarios such as different kinds of edge device. So what is the key optimization goal that we have to achieve when we do the software and hardware optimization? And here shows the key goals, that is the energy efficiency. So back in the AI1, which is perceptive intelligence, all we do is to optimize the TOS per watt, right? Because all these CN or IR models, they are all need many computation capability. But when it comes to the AI2, in the cognitive intelligence, we use transformer models to transform all the data into the token space. So the energy efficiency means that you can use a restricted power to generate more tokens. So the tokens per joule is a more important criteria when we try to develop a new system or a new hardware. So here shows our website to collect all the data, not only in the DN accelerator, but also on the LM accelerators. So if you're interested, you can feel free to scan our link and go to see our website. So right now, there are 3 typical applications in AI2. Text-to-text, text-to-image, and text-to-video. So today I will introduce 2 typical applications. The first one is the text-to-text, and in other words, it's about LM acceleration. So, and it is a typical memory-bound application. And on the other side, we try to also introduce our work on accelerating text-to-video, and it is a very compute-bound application. So we try to see that if FPGA can suit both for the memory-bound application and also the compute-bound application. So the first word I would like to introduce is FatLM. It is an efficient large language model inference accelerator with a complete mapping flow on FPGAs. It is our first work when we try to accelerate large language models on FPGA, and it is published in FPGA 24. And here shows some key ideas when we try to accelerate LMs on FPGAs. So the basic idea is that we know that when we try to generate tokens, it is mainly memory bounded, right? So the first idea that maybe we can try to reduce the memory access so that we can use methods like quantization and specification to reduce the workload. And the second one is that we try to boost the bandwidth utilization, so we can do different kinds of memory optimization technique so that we can get a better bandwidth utilization. And you can see on the left that there are some features in LM that we can use. One basic idea is that in the decode stage, there are many small intermediate activations. They are typically less in about tenths of gigabytes. So we can store this intermediate data on the FPGA on-chip SRAMs. And on the other hand, for models like nearly about 70 billion size, we see that they can gain an unstructured sparsity. We can benefit more accuracy. So based on these 2 insights, the first one we use is to use a structure N2 M sparsity so that we can develop a better structure to gain a better compute utilization. And on the other hand, we we use always on-chip decoder so that we can store all the intermediate data and also with mixed precision to boost the bandwidth utilization. And here shows our sparse DSP chain design. So to accelerate the end-to-end sparse pattern computation, we design a configurable sparse DSP chain to take advantage of the end-to-end sparsity characteristic. For high DSP utilization, we add sparse marks to filter out zero-element multiplications. And in order to keep the accumulation results correct, we also design the reduction node to dynamically select data output. As shown in the figure below, the configurable sparse DSP chain can fully utilize the non-zero elements. And here shows our second technique, layer fusion object inference with mixed precision. So due to the small activation in the decode phase, the repeated reading and writing of the activation value is avoided by layer fusion in the decode phase. So basically, we can keep all the activation values in the object cache at all times and reducing those inefficient object accepts. And at the same time, we apply mixed precision to the LM models. For example, we can apply int 8 or int 4 for the weight and int 8 for the activation for the linear layers. And also, we can apply int 16 or floating point precision to the attention or to the nonlinear operators. Using these mixed precision models, we can first attain the precision and also to reduce the number of sets. So here shows our demo to implement our FedLM on the U280 FPGAs. And we can see that FedLM with 16 nanometer U280 FPGA can outperform advanced 12 nanometer V100 GPUs in terms of a better throughput and a better cost efficiency and also high energy efficiency. And basically the inference speed is about 50 to 55 tokens per second. And since the FPGA is better and lower power, so we can achieve a six times higher energy efficiency than the GPUs. So to sum up, why we can outperform GPUs in decoding rather than prefill. And as is shown on the left, even if we apply like sparsification and quantization optimization, there's still about 10 times gap when it compared with V100 GPUs. But as I mentioned, that the decoding phase is more important when you do the LM acceleration, because nearly 90% of times is doing the decoding, and in this stage it is memory bounded. So FPGA is good at memory processing and also those data processing. Since FPGA, you can treat it as a near data processing platform. So in this work, we show that FPGA can surpass GPUs on decoding with quantization, sparsification, and etc. While prefill still requires some new exploration. For example, like prefill and decode disaggregated acceleration. So for the next work is our latest work on accelerating video generation models with online sparsification and hybrid precision. So it follows a similar technique like software and hardware co-design, but as I mentioned that video generation model is a compute bound. As I mentioned before, that LM is more memory bounded, and it still has about a large gap when compared with GPU in the preview stage. So is there any chance that we can use FPGA in those compute bound scenarios? So we try to answer that question in this work. And this work is accepted by FPGA 25, and it received the Best Paper Award. So I'll try to give a little background in terms of video generation. So we envision that large models will be more important in multimodality. So large models have brought change to the traditional production mode of films, game, virtual reality, and many technology companies are also actively deploying in the field of video generation. So we think it is a key modality and a promising path towards simulating the physical world. So when we try to assess this video generation, we try to draw on the ideas of traditional video compression film. So the basic idea is to divide the video into blocks and explore the similarity and importance between those blocks. In this way, the division sparsity technique and mixed precision condensation can be used to efficiently process different blocks. So here shows our key idea is to employ the spatial and temporal online activation specification to element redundant computations in video generation models. So the basic idea is to reduce redundant computations by leveraging inter and intra-frame similarity. As shown here, we can see that those two tokens are quite similar, right? So we can skip those similar tokens on the fly, and we also up to calculate the similarity between them so that we can know which kind of token and batch can be skipped. So to sum up, here to shows the experimental results. Our work FlatVGM achieves like 1.3 times speed up and 4.5 times energy efficiency enhancement compared to the NVIDIA 3090 GPU. And we try to point out that the original 3090 GPU peak performance is like about 21 times better than FPGA. When we use our specification, condensation, and also the scheduling optimization, we can get about like 29 times improvement when we compare with the original FPGA design. So we got a end-to-end like 1.3 times better throughput improvement. And we have successfully outperformed GPUs in performance on the current FPGAs that are not equipped with AIE. So we can see that using our software and hardware core design, even in a compute-bound application, FPGA can still get a better improvement over GPUs. So when we can have a hardened AI engine, for example, like when we can combine the HBM with AIEs, maybe we can get a further like 7 to 8 times improvement in the video generation model. So we believe there's many more work we can do in the future. So to sum up, we believe that AI optimization requires full stack collaboration across algorithms, software, hardware, and manufacturing. So by applying techniques such as pruning, quantization, and compilation optimization, and also some advanced technology, we can reduce computation workload, enhance peak performance and utilization with lower hardware costs. And we believe that in the generative AI area, software and hardware optimization is more and more important. And we can use this method to further reduce the inference latency and also the system cost. That's my talk today. Thank you.